In this slidecast, we'll talk about some additional stack applications. And we're going to focus on postfix and infix notation. This section is related to the programming lab you're going to do. So I encourage you to go to your book and study all the code that's available. You'll be able to reuse some of that in your lab, and you'll be able to adapt it. Now, postfix and infix notation, expressions are normally written in infix form. For instance, this column has expressions in infix form, and this is the form we're probably most familiar with. This is what we typically use for mathematical expressions, where we have the binary operators between the two operands. Now, it's easier for a computer to evaluate an expression in postfix form, since there's no need to group sub-expressions in parentheses or worry about operator precedence. So we'll write a class that evaluates a postfix expression containing digit characters and operator characters. These are the operators. And the space character is a delimiter between the tokens. So we're going to have an operand stack, which is the stack of operands. And these will just be int objects. We'll have an eval function that takes a string expression, and it returns the integer value of the expression. And we'll have a private function eval op that takes a character and it pops two operands and then applies the operator op to its operands and then returns an integer result. So this input op is the operator. Now the Boolean is operator returns true if the character, the input, is an operator symbol. We're going to use the stack to save operands until their associated operator is scanned. And the idea is we'll pop the operands, we'll compute a result, and then push the result back onto the stack. We're going to assume binary operators, and we'll disallow negative operands. So here's an expression. Here's the algorithm to evaluate it. So let's walk through step by step. So we empty the operand stack. And while there are more tokens, and there are an expression, we'll get a token. We'll get the 4. If the first character of the token is a digit, then we'll push the token on the stack. And it is a digit, so we will push a 4 on the stack. We'll skip back to the beginning of the while loop. There are more tokens. We'll get another digit, which we'll push onto the stack. So now 7's at the top of the stack. We'll get the next token. It's not a digit, but it is an operator, the multiplication operator. So we'll pop the right operand off the stack, and then we'll pop the left operand off the stack, and then we'll evaluate the operator, 4 times 7, which gives us 28, and we'll push the result back onto the stack. Now we continue our while loop. We'll get a 20, we'll push that onto the stack. We'll continue to the next token. It is an operator, so we'll pop our right and our left hand operands off the stack. We'll evaluate the operator, 28 minus 20. Gives us a result of 8, and we'll push that back onto the stack. Now there are no more tokens, so we'll exit the while loop, and we pop the stack and return the result. So 8 is the result of this expression. Here's some C++ for a postfix evaluator class. It has some public functions that are eval function, and then the private functions eval op and is operator. We have a syntax error class that inherits from invalid argument. And here's its constructor. Here's the implementation of our postfix evaluator function. And here's our eval method. You should look these class implementations over carefully in your book. Here's the eval op implementation that checks to see that the stack shouldn't be empty. It gets the left and the right hand operators, and then depending on the kind of operand, it computes the result and returns a result. Now to test this code, we could write a driver that creates a postfix evaluator object and reads one or more expressions and reports the result. We should catch syntax errors. We should exercise each path by using each operator. We should exercise each path through eval by trying different orderings and multiple occurrences of operators. And then we should catch any syntax errors, such as an operator without operands, a single operand, an extra operator, a variable name, the empty string. So all of these should throw syntax errors. Now to convert from infix to postfix, we'll assume that expressions consist of only spaces, operands, and operators. The space is the delimiter. All operands are identifiers that begin with a letter, and all operands that are numbers begin with a digit. So here's an example. So now we're doing expressions that don't just involve iterators, but they have variables. So here's the infix form, and here's the corresponding postfix form. And we're going to write a program that will take an infix expression and produce its equivalent postfix. For expressions without parentheses, there's two criteria to determine the order of the operands. Operators are going to be evaluated according to their precedence or rank, and the multiply, divide, and mod, the multiplicative operators, are going to be evaluated before addition and subtraction. And operators with the same precedence will be evaluated left to right. That's the left associative rule. Now, by temporarily putting operators on the stack, then we can pop them when they're needed and insert them into the postfix string in an order that indicates that they should be evaluated. So we're using our stack differently than the last example, because now we're going to put operators on the stack, not operands. So if we have these first two operators from the string, from this particular string, we would store them on the stack. We would push the minus, which we encountered first, and then the divide would be next. Now the operator divide, it must come off the stack and be placed in the postfix string before the operator minus. And if we have the stack as just shown and the next operator is times, we need to pop the divide off the stack and insert it into the postfix string, because the multiplicative operator scanned earlier should be evaluated before the multiplicative operator that was scanned later. We remember that left associative rule. So here are the data fields we'll have. We'll have a stack of operators. We'll have a postfix string that's being formed. A convert is a public function that takes an infix string as input and extracts and processes each token from that string and returns the equivalent postfix string. And these private functions are used in the implementation. We'll have a process operator, we'll have a precedence to get the precedence of an operator, and we'll have a Boolean isOperator function. So here's the algorithm for function convert. We'll initialize postfix to an empty string and the operator stack to an empty stack. And while there's more tokens in the infix string, we'll get the token. If the next token is an operand, then we'll append it to the postfix string. Otherwise, if it's an operator, then we'll call process operator to process the operator. Otherwise, we'll indicate a syntax error. When there are no more tokens, then we'll pop the remaining operators off the stack and we'll append them to the postfix in the order that they're popped off. Now the function process operator, if the operator stack is empty, then we'll push the current operator on the stack. If the precedence of the current operator is greater than the precedence that's on the top, then we'll push the current operator onto the stack. Otherwise, while the stack's not empty and the precedence of the current operator is less than the precedence of the operator that's on the top of the stack, Then we'll append the top of the stack to the postfix string and we'll pop the stack. Finally, we'll push the current operator onto the stack. Here's an example. Down this column, we'll read input from an input string. Here's the actions that we'll take. Here's going to be the picture of the operator stack, and here's the output string that we're building. So if we get a W, it's not an operator, so we'll just add it to postfix. When we get a minus, we'll push that onto the stack. When we get a 5.1, that again will go onto the stack. Now once we get the divide, and the precedence of divide is greater than the precedence of minus, so we'll go ahead and push that onto the stack. Then we'll scan in sum, which gets appended to the postfix string. Once we get the multiply, the precedence of multiply is equal to the precedence of divide that's on the stack. So we're going to pop off the divide operator, and we'll append that to the postfix. And now since the precedence of the multiply is greater than the divide, then we'll push the multiply onto the stack. Finally, we read a 2, and we append that to the string. Now we're at the end of the input, but the stack isn't empty. So we pop multiply off the stack, and we append that to postfix. And then we pop the minus off the stack and append that to postfix. So this final answer here is our original expression in postfix form. Here's the infix to postfix header file. We'll either use the author's stack class or we can use the standard library. And we'll have this class infix to postfix with its public functions. And we've got some private functions. We have a precedence function that takes an operator and then it returns the value from a precedence array indicated by the return from this find OP function, which finds an operator from this list of valid operators. And here are the data fields. We'll define a stack, and we'll have this precedence array. So here's the implementation of our infix to postfix class. And we've got some constants defined for the operators and their precedence. Notice here's an array that keeps track of the precedence of our plus, minus, multiply, and divide. And here's the convert function. Here we call a function to see if the next token is an operator. Here's where we look up the precedence of the operator, and we compare it to the precedence of what's on the top of the stack. And here's where we're popping the stack for all the operators that are equal or higher precedence. Now to test this program, we need to use enough test expressions to satisfy ourselves that the conversions are correct for properly formatted input. So we could try different orderings, multiple occurrences of the operators, and we could try infix expressions where all the operators have the same precedence. And we would catch an exception for syntax error whenever that error is expected. So here's a test program, kind of a main that's a driver. We create this infix to postfix instance. We prompt the user for an expression, and then we convert that expression to infix, and we output the result. And notice we're using the try catch to do exception handling. The ability to convert expressions with parentheses is an important and necessary enhancement. Parentheses are used to separate an expression into sub-expressions. So we can modify process operator to push each opening paren onto the stack as soon as it's scanned. So now we're going to have both operators and the parentheses will go on the stack. And when a closing parenthesis is scanned, we should pop all the operators up to and including the matching opening parenthesis. and then insert all those operators in the postfix string. Now this will happen automatically in the following while statement if the precedence of the closing parenthesis is lower than that for any other operator except for the opening parenthesis. Okay, so study this code and see if you can confirm kind of the claim here of what's going to happen. Now a closing parenthesis is considered processed when the corresponding opening parenthesis is popped from the stack and the closing parenthesis is not put on the stack. So the following if statement executes after the while loop exit. So if an operator is the closing paren and the stack's not empty and the top is equal to the opening, then we'll pop the stack. The implementation of infix to postfix that processes parentheses, that's in your book. Here's the include statements and the using statements for namespaces. To test this, we could use the classes developed for the prior case studies to evaluate infix expressions with integer operands and nested parentheses. So our program driver would need to create instances of both classes and apply the function convert to the infix to postfix parens object. And the argument for convert is an infix expression and the result will be in postfix form. So next the driver will apply the function eval of the postfix evaluator object. And the argument for eval is going to be the postfix expression returned by convert. And we need to make sure there's space before and after each parenthesis so that it can be parsed correctly. And that brings us to the end of this slidecast and the end of Chapter 5.